about Hess's law. Okay. When we're talking about Hess's law, we are, or not Hess's law, I'm sorry, that was last chapter. When we're talking about equilibrium isn't where your products and your reactants are equal amounts. Okay? A lot of times people get to the point where they think that equilibrium is where you have an equal amount of reactants and products. Hang your head. Okay, that's not the case. We established up there what we would term as equilibrium. So we had, with our paper throwing, we had our reactants, we had our products, and we were pretty much, we started at 60 here, okay? And, the first couple, we ended up, let's just kind of combining those, let's say 49 and 11, okay? And then eventually we got to the point where we had 45 and 15 and then 44 and 16. And if we would have kept going, it would have stayed right around this same amount here. Okay? Because we had so many people on this side compared to this side that you were going to get that back and forth motion where they were just going to end up with a few things and they were going to end up with the same, more. And that's what equilibrium is, where you end up where you're producing about the same amount of each thing. Okay. And equilibrium is where you have a reversible reaction. Okay. So you've probably seen a few times, and when we talked about weak acids earlier this year, we always use these back and forth arrows. Okay. And that's where you're producing some of this, and you're also producing some of this, and some of this is becoming that, and it keeps trading off back and forth. Okay. When that trade-off has equalized the amount of this stuff being made compared to the amount of stuff being made here, when that equalizes, then you're at equilibrium. But it doesn't mean that you have the same amount of products and reactants necessarily. It's a very rare case that happens. Usually one side is favored over the other. Okay. In this case, because we have more reactants, they are going to be favored over the products. Okay. So you're keeping more stuff on this side than you are on this side. All right. And, like here's an example of a reversible reaction. You've got some of it is liquid, some of it is gas. So in your little water bottle that you have at your table, probably, okay, some of that, you've got your water sloshing around down in here. But up here, you've got a few of those that are water molecules. And they're going to be trading back and forth. This guy's going to become liquid, and one of these will become, and it's a back and forth trade-off. Okay. And then they go through a few other examples here of that. This is called then dynamic equilibrium. Okay. It's where the rate, so we're looking at rates, getting back into rates here, which is kinetics. That was unit 5. The rate of the forward reaction is equal to the rate of the reverse reaction. Again, not the amounts. It's not the amounts that are equal. It's the rates that are eventually equal. Okay? That trade-off is equal in the rate. Equilibrium is dynamic, meaning that the reactants and products are constantly being formed but they're formed at the same rate. Okay. Oh, this is a better drawing of water evaporating as opposed to my pathetic drawing, because we know what kind of an artist I am. I work in fabric and thread, not in this dimension. All right. So here is a graph that shows equilibrium. When we started, our products had 0 balls of paper and our reactants had 60. And we could have snapshotted that earlier than 30 seconds, okay? But at any rate, we eventually ended up leveling off here where we had, and our graph would have looked a little different than this. Our graph would have looked like this, where we had our reactants and they leveled off up here, and our products, they leveled off down here, because they ended it with like 45 and you guys with 15. So they don't necessarily cross here. It just depends on how much stuff you're producing. In this case, your products would have been favored because you would have ended up having more of them than the reactants. In your case with the snowballs, or your paper balls, whatever you want to call, like, we could have gone out and done snowball fights, couldn't we? Yeah, a tad bit. I'm sure that the school would have probably frowned on it too. So.
Really? Yeah.
But at any rate, this one, our reactants were favored. Okay, so that's the idea behind what equilibrium is. And like I said, yeah.
So is the equilibrium line like when the two
when they get
parallel?
straight? Yep, when they're parallel. So you've hit that. They found here approximately where they started. They were at parallel points, and that's where your equilibrium is. So that's what you're looking at in the graph.
So is your equilibrium the two lines, or is it the dot where they?
This is where equilibrium is established, and everything from here over. So this whole section here is at equilibrium. Good. Good. All right. So here we're given a reaction. We have A and 2B, and they give us C and D. So the reaction is going to start with 1 atm of A, 1 atm of B. There is no C or D in the flask. And we're going to sketch a graph to show that it proceeds at equilibrium. And when it does, we have 0.8 atm of A. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is going to be our 1. This is going to be our 0.8. This will be 0.6, 0.4, 0.2, and that'll be 0. All right. So we're starting out with A and B up here. So there's my A, and we had 1 of B. I'm going to try to change colors here for B. So I've got a B here as well. I'm just trying to nudge them side by side. And then C and D, since they are both in 1-to-1 ratios, I'm just going to do them as one color because they're going to be the same amount anyway. Does that make sense? All right. So I have A is going to get used up, and I'm going to end up with 0.8 of it. So I'm going to start with my A, and that was red. I'm going to start here, and I'm going to take it, and I'm going to go down and down and down until I can get a parallel line here with 0.8. Okay. Now, B is going to get used up at twice the amount. So how much am I, if I use up 0.2 of A, How much of B am I going to use up? 0.4, which would take me down to 0.6. So it's going to be down here. And I'm going to try to get that drop. All right. If this used up 0.2, so if I do my BCA table here, A plus 2B yields C plus D. I started out at 1 and 1 and 0 and 0. This I would have used up 0.2, which left me with 0.8. Here I would have used up 0.4, which left me with 0.6. Here I would have added how much? How much am I using over here? I went up into the cloud, right? The cloud is 0.2. So I come back down. How much am I making of this? 0.2, which means I have 0.2 made of this, and I'll have 0.2 made of that as well. So I'm going to take this guy, and I'm going to take him up, and I'm going to, it's probably not the best. Let me try to redo that. Okay, I'm going to try to get him at equilibrium right about here. Sometimes it's easier to do your parallel line first and then connect them up. All right. So upon reaching equilibrium, there's 0.8. They wanted us to finish this graph. We have. We are going to find where our equilibrium is. And our equilibrium, like Presley said, is where this line, all these lines become parallel to one another. So from here over, we are at, so this whole section here is going to be at equilibrium then. Let me see if I can highlight that. Oh, no, it just lets me highlight text. Never mind. That would be too handy. See if I can draw a circle here. It'll let me draw a circle. Yep, that whole section in there then is equilibrium. Make sense? All right. A little BCA table going on there. All right, let's keep going here. Write an equilibrium reaction for the following processes. Oh, I have line selected. I need to draw. There we go. So freezing and melting of benzene. So freezing, C6H6. That would be, if we're freezing, what would it start as? A liquid. And we are freezing it, so we are going to become a solid. Easy enough. And this is a back and forth reaction. Some of it, this is at the freezing point. So some of it's freezing, some of it's melting. Back and forth and back and forth. All right, let's switch pen colors here just to be fun. Dissolution of HCN aqueous. So HCN aqueous. What's dissolution mean? Yep. We're going to take it out of an aqueous situation and we're making it solid. I feel like blue for the next one. All right. I'm starting with HS minus. And on the other side, and that's aqueous, on the other side, I'm going to have H2PO4 minus aqueous. We got to figure out what other partners are here. Okay. So this guy over here is going to be donating a hydrogen here. What's left behind? If this hydrogen leaves, what do you have left? S minus. If this gained a hydrogen over here, what did it start with over here? H, PO4. I was a minus here, and I have an extra hydrogen, so what would it be for your charge? -2. And that would also be aqueous. I lose anybody? Good? Makes sense? Everybody happy? All right. We shall direct our attention then to 7.2. Direction of reversible reactions. All right. In a reversible chemical reaction, the reaction reached equilibrium when the rate of the forward reaction is equal to the rate of the reversible reaction. And remember, it's these rates that we're worried about. Okay, not quantities. When the rate of the forward reaction left to right is greater than the reverse reaction, the reaction is not at equilibrium. The products are being made faster than the reactants. So there's a net gain for the products. So when we first started out, you guys had 60 of these and you had 0 of these. We're going to be making more of these than we would these, just because we've got to keep going, okay, till we balance. The net gain in the amount of products will occur until the reaction reaches equilibrium. And then at the equilibrium amount, both reactants and products remain constant. So we got to that point where we were essentially at 45 for our reactants and our products were around 15. And the rate is equal, not the amounts, the rate. The same is true when the rate of the reverse reaction is greater than the forward reaction. Okay, if we would have started out with more reactants than products, more products than reactants, then this, would have been flipped around. All right. So we've got a reaction here. We are going to be adding in some of this stuff. What's going to happen to the rate of the forward reaction? So we're dumping more of this stuff in. So I'm giving these guys more, I'm giving the products more stuff. What's going to happen to the reaction that's going this way, that's forming more products? Yeah, it's going to slow down. Good. And what's going to happen to the reaction that's going this direction then? It's going back this way. You're dumping more of this stuff in. What's going to happen to this reaction? Yep. The reverse then is going to speed up. Will they eventually end up reaching equilibrium? Yeah, eventually they will. But it's just going to take a little bit of time to kind of catch that up and get that equilibrium reestablished. All right. We have a 1 liter flask. We have 0.4 moles of A. I think A was, what color was A before? Red. So 0.4 moles of A. So I'm going to do A as red. We have 0.5 moles of B. B is up here. So B is going to be green. And it comes to equilibrium. So this is, we're using up at equilibrium, there were 0.5 moles of C. So C was this yellow color. 0.15 would be right here. So at equilibrium, we're going to be here for C. Okay, so I can draw that and get that to establish equilibrium. I've got to figure out how much of these guys were used up to get to that, though. So if I made 0.15 of C, I would have had to have used up 0.15 of A. And I started with 0.4. So that's going to leave me with stupid computer. 0.4 minus 0.15 is 0.25. Gosh darn thing. 0.25. So that's my A is going to end up at 0.25 for A. A was green. A is red. Lippy, bad Lippy. Bad Lippy.
Lippy goes.
So right there is where A is going to end up at. And then for B is we started out with 0.5 of that. If we used up 0.15 of A, how much of B are we going to use up? 0.3, because we're going to use it up at twice the amount because it's in a 1-to-2 ratio. That's going to leave us with 0.2 of B. So B is going to end up right there. So now I'm going to try to draw my line going down there. All right. Now. Oh, that was easy. That's it. Oh, I thought we were going to have to do more. That wasn't too bad. Okay. All right. So I want for the weekend, I want you to get 7-1 and 7-2 done. And, you know, you've got about 10 minutes to get started on it. Again, come and talk to me, please, if you think I erred in any way.